The Tehachapi Pass cuts through the Tehachapi Mountains at an elevation of 3,793 feet, connecting California's Central Valley to the Los Angeles Basin. The Southern Pacific Railroad threaded this gap in the 1870s, building 28 miles of track that climbed 2,734 feet through 18 tunnels and a continuous series of curves. The famous Tehachapi Loop, where the track circles back over itself, was an engineering solution to mountain grade limitations. By 1952, this single corridor carried nearly all rail freight moving between northern and southern California. Timber, agricultural products, petroleum, and manufactured goods traveled this route daily. The pass handled approximately 40 trains per day in both directions. No parallel route existed with comparable capacity. Winter weather was routine. Snow fell most years between November and March. Railroad crews maintained rotary plows, flangers, and spreader equipment designed for mountain operations. The pass closed occasionally, usually for hours rather than days. Maintenance schedules accounted for winter delays. The rail line represented a fundamental assumption in California's transportation infrastructure. The mountains would slow traffic, not stop it. Tehachapi Pass was a bottleneck by geography, managed through operational practice. The railroad's engineering and clearing capacity had matched winter conditions for 7 decades. January 1952 began within normal parameters. Trains moved through light snow. Temperatures dropped, but not unusually. The pass remained open. The first substantial storm system reached the Tehachapi Range on January 12, 1952. Snow fell steadily, but not dramatically. Accumulation measured 6 to 8 inches in the pass. Temperatures remained in the teens and 20s Fahrenheit. Railroad crews deployed plows and kept the line clear. Train schedules slowed but held. Northbound and southbound traffic continued with minor delays. Snow removal followed established protocols. Rotary plows broke through drifts. Spreader cars pushed snow off the roadbed. Section crews cleared switches and signals. The system functioned as designed. A second storm arrived on January 15. Another 8 inches accumulated. Clearing operations intensified but remained routine. No trains were stranded. The railroad issued no special bulletins. This was mountain railroading in winter. Additional snowfall came on January 18, then again on January 20. Each storm added 6 to 10 inches. The intervals between storms shortened. Ground temperatures prevented melting. Each new layer bonded to the previous one. Total accumulation in the pass exceeded 30 inches by January 21. Snow depth alone did not trigger alarm. The railroad had cleared deeper snow in previous winters. Crews worked in shifts. Equipment remained operational. The pass stayed open. What changed was persistence. Snow fell, crews cleared it, and snow fell again before the roadbed fully dried. The mountains began holding snow faster than the railroad could remove it permanently. The cycle accelerated. Wind velocity in the Tehachapi Mountains routinely exceeded 30 miles per hour during winter storms. The pass formed a natural wind channel between the Central Valley and the Mojave Desert. Air compressed as it moved through the gap, accelerating across open ridges and into track cuts. Snow in motion behaves differently than fallen snow. Wind-driven snow filled cuts and depressions faster than gravity alone could distribute it. Drifts formed wherever terrain or infrastructure interrupted airflow. Track sections that had been clear at the end of a work shift were impassable by morning. The railroad's track geometry created drift zones. Curves banked into hillsides concentrated wind-blown snow. Cuts designed to reduce grade captured moving snow like channels. Tunnel approaches, where track transitioned from open air to enclosed space, became accumulation points. Wind deposited snow precisely where trains needed clear passage. Rotary plows could break through drifts, but clearing required time. A drift 20 feet deep and 50 feet long might take an hour to cut through. While crews cleared one section, wind refilled previously cleared areas. Forward progress slowed. The wind also affected snow density. Packed, wind-hardened snow resisted removal equipment more than freshly fallen snow. Plow blades encountered consolidated material that required multiple passes. Equipment strained against loads exceeding design expectations. Between January 22 and January 25, sustained winds above 25 miles per hour accompanied continued snowfall. Drifts exceeded rail car height in multiple locations. The pass remained technically open, but transit time through the corridor tripled. Temperature patterns in late January prevented any melt cycle. Daily highs remained below freezing throughout the pass. Nighttime lows dropped into single digits Fahrenheit. Snow that fell on January 12 was still present on January 28. Sequential storms continued. Snow fell on January 23, January 26, and January 29. Each storm added between 4 and 12 inches. Total measured snow depth exceeded 60 inches in uncleared areas by the end of January. Even maintained track sections carried several inches of compressed snow and ice. The snow's physical properties changed over time. Lower layers compressed under the weight of newer accumulation. Ice crystals bonded into denser structures. What began as powder became something closer to névé, the granular, partially consolidated snow that precedes glacier formation. This material could not be blown away or easily displaced. Railroad maintenance equipment operated continuously. Crews worked 12-hour shifts without clearing the backlog. The railroad brought in additional rotary plows from other divisions, but the pass's narrow working space limited how many machines could operate simultaneously without interfering with each other. Storage became a problem. Cleared snow had to be moved completely off the right-of-way. In deep cuts, this meant throwing snow vertically 15 to 20 feet. Plows could cut through snow but had limited capacity to remove it from the corridor entirely. Snow piled on slopes sometimes slid back onto tracks. By February 1, the railroad faced a fundamental equation. Snow arrived faster than it could be permanently removed. The corridor was narrowing. The Tehachapi Pass route was never designed for extended closure. Its engineering solved the problem of crossing mountains with the grade limitations of steam-era locomotives. Maximum grade reached 2.2%, steep for railroads, but manageable. The continuous curves, however, meant that sightlines rarely exceeded a few hundred feet. Track curvature creates specific snow problems. Snow accumulates differently on the inside and outside of curves due to wind patterns and centrifugal drift from passing trains. Clearing equipment must follow the curve, limiting the width of each pass. Curves also prevent long sight distances, complicating operations when multiple clearing machines work the same section. The Tehachapi Loop itself, where track circles 360 degrees, rising 77 feet while crossing over itself, became a critical vulnerability. Snow filled the loop's interior and approach cuts. The continuous curve meant clearing crews had no straight sections where they could build momentum. Each pass through the loop required careful, slow work. Tunnels presented different challenges. Snow entering tunnels from either portal created blockages in confined spaces where equipment maneuverability was limited. Several tunnels accumulated ice on their ceilings and walls from freeze-thaw cycles of snow melting and refreezing. Clearance margins shrank. By early February, specific locations became impassable despite continuous clearing efforts. Tunnel approaches remained choked. The steepest grades held compacted snow that equipment could not fully remove. Multiple trains stalled attempting to climb sections where snow depth reduced traction below operational thresholds. The railroad began rerouting traffic away from Tehachapi, adding hundreds of miles and multiple days to shipping schedules. Some freight couldn't reroute at all. Railroad signals operated on electrical systems requiring clear mechanical movement and unobstructed sightlines. The Tehachapi line used semaphore signals and electric switch points powered by lineside batteries and small generators. Snow and ice disabled both. Switch points, the movable rails that guide trains from one track to another, froze in position under accumulating snow and ice. Section crews attempted to keep critical switches clear, but sustained cold prevented complete success. Even cleared switches refroze within hours. Manual operation was possible but slow, requiring crews to physically throw each switch and confirm alignment. Signal visibility disappeared under snow load. Semaphore arms iced over. Lamps became obscured. Signal wires carrying electrical impulses froze or broke under ice weight. With signals unreliable, train movements defaulted to manual authorization, dispatchers issuing written orders to crews, who proceeded at restricted speeds under line-of-sight rules. Restricted operation reduced capacity. Trains that previously moved through the pass at 30 to 40 miles per hour now advanced at 5 to 10 miles per hour, with frequent stops for switch operations and signal confirmations. Transit time through the 28-mile corridor expanded from under 2 hours to 6 or more hours. Telegraph lines carrying dispatcher communications failed in several locations. Repair crews reached some breaks, but others remained inaccessible due to snow depth. Communication gaps meant sections of track operated under local control only, with no coordination across the entire pass. Power for electric infrastructure came from small generating stations along the line. Some became snowed in. Crews manually dug out facilities, but fuel delivery to isolated stations became problematic. Several stations ran on reserve power for extended periods. A freight train stalled on a mountain-grade transitions from operational equipment to stranded infrastructure. On February 3, a 70-car northbound freight lost traction climbing through fresh snow near the Tehachapi Loop. The locomotive crew attempted to reverse and take another run, but snow behind the train had drifted during the stall. The train could not retreat. Additional stalls followed. A southbound train attempting to assist the first became immobilized when snow depth exceeded plow clearance. By February 5, 7 trains sat stationary at various points in the pass. Some had been stopped for more than 48 hours. Crews remained with their trains initially. Conditions deteriorated. Temperatures dropped below 0 Fahrenheit on the night of February 6. Locomotive coal supplies ran low. The railroad organized relief efforts, bringing food and fuel to stranded crews on foot and by track maintenance vehicles. Several crews were eventually evacuated when it became clear their trains would not move for days. The stranded trains created obstacles for clearing operations. Plows could not pass stalled consists. Work had to proceed around them. In some cases, stranded trains blocked the exact sections that needed the most intensive clearing. The railroad considered uncoupling cars to create passage points, but determined the risk of equipment damage in deep snow was too high. Each stalled train represented cargo not reaching its destination. Perishable goods froze or spoiled. Time-sensitive shipments missed delivery windows. The economic cost compounded daily. The trains themselves began disappearing under continued snowfall. By mid-February, some consists were visible only as vague shapes under snow mounds. The Southern Pacific Railroad committed all available resources to clearing Tehachapi Pass. Rotary plows from Oregon, Nevada, and Northern California divisions were redirected to the mountains. Crew counts exceeded 300 men working in continuous rotation. The effort represented one of the largest snow-clearing operations in the railroad's history. Mechanical rotary plows attacked drifts methodically. Each machine consisted of a revolving wheel with cutting blades, powered by a dedicated locomotive. The wheel cut through snow, throwing it to the side via an adjustable chute. In optimal conditions, a rotary plow could cut through 10 to 12 feet of packed snow at walking speed. Conditions in Tehachapi Pass were not optimal. Snowpack exceeded 15 feet in multiple locations. The combination of wind-compacted upper layers and weight-compressed lower layers created stratified resistance. Plows frequently stalled, requiring reverse and repeated passes. Cutting rates dropped to fractions of a mile per day in the worst sections. Equipment failures increased. Rotary blade assemblies designed for intermittent use ran continuously for days. Bearings overheated despite cold conditions. Drive chains stretched and snapped. Boiler pressure struggled to maintain power in sustained operations. Repair crews worked alongside clearing crews, but replacement parts had to be brought in from outside the pass, another logistical delay. Human limits appeared. Crews worked to exhaustion. Frostbite cases increased. The railroad established heated shelters at intervals along the line, but men working directly on clearing operations often went 8 to 10 hours between warm breaks. Productivity declined even as effort intensified. By February 10, the railroad had cleared approximately 9 miles of the 28-mile corridor to operational status. 16 miles remained blocked or marginally passable. Snow continued falling intermittently. Los Angeles and other Southern California ports depended on rail connections to inland production zones. With Tehachapi Pass closed, freight normally moving through the corridor backed up at both ends. Rail yards in Bakersfield and Mojave filled to capacity with waiting trains. Cargo rerouting had limits. The coastline route through San Luis Obispo added 180 miles and required crossing additional mountain grades. Capacity on that line was already committed to regular traffic. Absorbing Tehachapi's volume was impossible. Some freight shifted to trucks, but 1952 highway infrastructure could not replace rail tonnage. The roadways themselves were also impacted by snow. Industrial impacts appeared in measurable form. Lumber mills in Northern California accumulated inventory with no outlet. Agricultural shipments from the Central Valley faced delays reaching southern markets. Petroleum refinery operations adjusted production schedules based on distribution constraints. Manufacturing plants in Los Angeles region reduced shifts as raw material supplies tightened. The Port of Los Angeles recorded a 16% decrease in outbound rail freight during February 1952 compared to the previous year's monthly average. Dock workers faced reduced hours. Ships waited longer for cargo assembly. The ripple extended to Pacific shipping schedules. Passenger service also suffered. The Southern Pacific San Joaquin Daylight, a named passenger train serving the valley-to-coast route, canceled multiple runs. Alternative routing added 6 to 8 hours to travel times. Passengers stranded mid-journey required hotel accommodations at railroad expense. Economic estimates varied, but freight delays and rerouting costs were calculated in millions of dollars by late February. No single catastrophic loss occurred, but the cumulative drag on California's economy was measurable in statistical terms. U.S. Highway 466 crossed Tehachapi Pass roughly parallel to the railroad, serving as the primary automobile route between the Central Valley and Southern California. The highway closed to all traffic on January 28, 1952, and remained closed for 19 days. Snow depth on the highway matched or exceeded conditions on the railroad. The California Division of Highways deployed plows and graders, but the equipment available in 1952 was less powerful than railroad machinery. Road clearing progressed more slowly. Several highway sections became completely impassable when drifts hardened into ice masses that required manual braking before mechanical removal could begin. The highway closure eliminated the alternative route that might have absorbed some traffic displaced from the railroad. Trucks carrying time-sensitive cargo sat idle. Passenger vehicles detoured through desert routes, adding 200 miles to trips. Some travelers became stranded in small mountain communities. Mountain communities themselves faced isolation. Tehachapi, Keene, and other settlements along the pass depended on highway access for supplies. The California Highway Patrol organized emergency supply runs using tracked vehicles and snowcats, but routine commerce stopped. Residents in higher elevations spent weeks with limited outside contact. Schools closed. Medical access became a concern, though no emergency medical crises were recorded during the closure. Propane and fuel oil deliveries were prioritized to prevent heating failures in occupied structures. The small population in the immediate pass area, perhaps 2,000 people, waited. By mid-February, both the railroad and the highway remained closed. California had no functioning surface transportation corridor through the southern Sierra Nevada and Tehachapi ranges. Air transport was unaffected, but could not replace ground freight capacity. The Southern Pacific's clearing operations evolved into an endurance test. Progress was measured in hundreds of feet per day rather than miles. Each section cleared represented a small victory that might be undone by the next storm. Crew rotation became formalized. Teams worked 6 hours on, 6 hours off, in continuous cycles. Heated barracks cars were positioned at multiple points along the pass. Food service operated around the clock. Medical personnel remained on site for cold injury treatment and general health monitoring. Mechanical innovation appeared incrementally. Crews modified plow chutes to throw snow at steeper angles, reducing the chance of material sliding back onto cleared track. Double rotary operations, 2 plows working simultaneously from opposite directions toward a meeting point, proved effective in specific locations. Compressed air systems were rigged to blow ice off signals and switches between manual clearings. Communication improved. Telephone lines were re-established through temporary above-snow installations. Dispatchers gained better situational awareness of conditions across the pass. Coordination between clearing sections increased efficiency marginally. The weather offered brief cooperation. A 4-day period in mid-February brought no new snow. Temperatures remained cold, preventing melt, but the absence of additional accumulation allowed clearing crews to gain ground. By February 18 of the 28 miles were rated passable for train operations. The remaining 10 miles held the deepest snow and most complex terrain. No one predicted rapid resolution. Railroad management issued statements that restoration of full service might require another 2 to 3 weeks. Crews maintained effort, but exhaustion was visible. Equipment breakdowns increased as machines operated beyond design endurance limits. The first through train moved the entire length of Tehachapi Pass on February 21, 1952. The northbound freight consisted of 41 cars carrying high-priority cargo that had been waiting nearly 3 weeks. Transit time through the pass was 9 hours. The railroad operated under severe restrictions. Single train movements only, daylight operations exclusively, manual signal confirmations at every control point. This was not full restoration. Clearing operations continued in parallel with limited train movements. Speeds remained restricted to 5 to 15 miles per hour depending on conditions. Only essential freight moved initially. Passenger service remained suspended. Highway 466 reopened to controlled traffic on February 23. One lane was cleared to minimum width. Travel was permitted only during daylight hours and only for vehicles equipped with chains. Full 2-lane operation would not resume for another week. Through the final days of February and into early March, capacity gradually increased. The railroad expanded to multiple daily trains, then began accepting lower priority freight. Restrictions eased incrementally. Stalled trains from early February were recovered, some requiring towing by multiple locomotives. Equipment was inspected for cold weather damage before return to service. Snow remained. Depths in uncleared areas still exceeded 10 feet in early March. The mountains would hold snow into May, but the transportation corridor was functional again, if compromised. Normal traffic volumes would not return until late March. The economic backlog took longer to clear than the snow. Delayed freight continued arriving at destinations weeks after expected delivery dates. Contract penalties were negotiated. Insurance claims were filed. Supply chain disruptions echoed through April as industries adjusted inventory to account for February's losses. California's transportation system had been constricted, not severed. The distinction mattered economically, but did not erase the fundamental lesson. The Southern Pacific Railroad documented direct costs exceeding $2 million for the Tehachapi Pass closure, approximately $23 million in 2024 dollars. This figure included equipment damage, overtime labor, emergency resource mobilization, and lost revenue from suspended operations. Indirect costs from cargo delays and contract penalties were not fully calculated but substantially exceeded direct costs. Freight delay impacts spread across industries. Lumber suppliers estimated losses near $500,000 from accumulated inventory and missed delivery windows. Agricultural shippers recorded spoilage and downgraded product value losses approaching $300,000. Petroleum distribution interruptions caused refinery scheduling changes that cost refiners and distributors approximately $400,000 in operational inefficiencies. The California Division of Highways reported snow removal costs for February 1952 at roughly $180,000, triple the normal winter maintenance budget for that region. Emergency supply operations to isolated communities added another $40,000 in state expenditures. Human costs appeared primarily as injury statistics. Medical records from Southern Pacific crews documented 27 cases of frostbite serious enough to require treatment, 3 cases of hypothermia requiring hospitalization, and numerous minor cold injuries. No fatalities were directly attributed to the closure. Highway travelers experienced similar injury patterns, though documentation was less complete. Operational statistics quantified the disruption more precisely. During the 3-week primary closure period, approximately 840 scheduled freight trains could not transit Tehachapi Pass, an average of 40 per day. Of these, roughly 60% were eventually rerouted, 30% were delayed and moved after reopening, and 10% saw cargo transferred to other transport modes or canceled entirely. The Port of Los Angeles recorded 23,400 tons of freight delayed by at least 2 weeks due to the closure. Regional manufacturing output in Southern California declined by an estimated 3% during February relative to January production levels, with the Tehachapi closure cited as a contributing factor in post-analysis reviews. The 1952 closure prompted infrastructure vulnerability assessments within the Southern Pacific Railroad and California state transportation planning agencies. Snow, previously categorized as an operational inconvenience in the Tehachapi region, was reclassified as a critical failure risk. The railroad modified its winter operational protocols for mountain divisions. Snow removal equipment allocations increased. Prepositioning of rotary plows before storm events became standard practice. Weather forecasting cooperation with the U.S. Weather Bureau expanded. Contingency planning included specific triggers for implementing restricted operations before conditions became unmanageable. Infrastructure improvements followed over subsequent years. Additional snow sheds were constructed at identified drift zones. Signal systems received upgrades to improve cold weather reliability. Heated switch installations replaced some manually operated points. Track geometry was modified in specific curves to reduce snow accumulation patterns. These changes occurred gradually through the 1950s, not as an immediate response. California's highway system planning incorporated the Tehachapi experience into design standards for mountain routes. The concept of redundant capacity, ensuring no single corridor could paralyze regional transportation, influenced route development decisions for the next decade. Interstate highway planning in the 1960s reflected this thinking. Economic planning also shifted. Industries dependent on rail freight increased inventory buffers to absorb potential transportation interruptions. Supply chain designs incorporated alternative routing options even when more expensive than primary routes. The concept of transportation system fragility entered corporate risk assessment frameworks. The pass itself remains. Tehachapi still carries freight trains through the mountains, now operated by BNSF Railway. Winter snow still falls, trains still slow, but the closure of 1952 established parameters. Snow depth times duration times corridor dependency equals systemic vulnerability. The mountains closed California once. The corridor reopened. The equation did not change.